So our next unit after forces and fields is our electromagnetic radiation unit, so dealing with light. So the question to start off with is, what is light? Now you're probably familiar with light that you can see. That's probably the most common form. But when we talk about light, we actually talk about an entire spectrum. So this next unit is dealing with the question of what is light. We are going to look at kind of the history of light, and the study of light, and also some of its implications for the physics around us. Now, this started back in ancient Greece, where they were already asking questions about what light was and coming up with explanations of kind of why we can see, why some things are larger than other things. And then as time went on, this is kind of where the main conflict and kind of where we pick up our study of light is where Newton and Huygens, where there was really two different schools of thought on light. One school thought that light was particles or corpuscles, and the other school thought that light was made up of wavelets. Now, Thomas Young did an experiment, a famous double slit experiment that we'll learn about, where he actually observed an interference pattern with light. Now, it was known at the time that interference patterns were they were things that waves did, and so that was kind of sold it that okay, light was a wave. But then Einstein came along later, and we saw some of these other particle properties that we'll learn about, and kind of said that light is a photon, which is both. So the answer when we say what is light, is it a wave or a particle? The best answer is to say, well, it's both. And so in this unit, as we move forward, we're going to learn about light's wave properties, light's particle properties, and why it's okay that it's both, and why it's important that it's both. Now, light, or electromagnetic radiation, has some important properties. Heinrich Hertz performed an experiment using an AC generator. So this is alternating currents. So here there was charge moving out from negative towards positive. So that's the direction of charge. And if we use our hand rule and the palms going in, that means that there's a magnetic field component into the page. Now this is alternating currents, so this would turn on and off. So this wave would continue on with that magnetic field component going into the page. And then when it switches direction, now the current's going to be flowing that way. And we're going to have a magnetic field component coming out of the page. And he had an apparatus set up where he could measure this and test it. He did this to confirm research that had been done by Maxwell. Now, there were some important implications to this, and that kind of brings us to our first big idea about electromagnetic radiation, and it has to do with the orientation of everything. When we talk about electromagnetic radiation, we have some direction that wave or particle, whatever you want to call it right now, is actually propagating. So it's moving in a certain direction, and it's made up of both electric and magnetic fields. That's why we call it electromagnetic radiation. Now, the important thing to keep in mind is that everything is perpendicular to everything else. So if we have our wave propagating in one direction, then the electric field component is perpendicular to that propagation, as well as the magnetic field, which is also perpendicular to everything else. So the magnetic field, the electric field, and the direction the charge is moving, or the electromagnetic radiation is moving, is all perpendicular to everything else. So that's important to remember, that everything is perpendicular. And that's just the nature of electromagnetic radiation, and we can measure that with devices, and it shows us that they are perpendicular to each other. The other thing, and this is kind of something we're going to look at today, is the speed of light. So all light, it doesn't matter if it's radio waves or it doesn't matter if it's X-rays, anything in what's called the electromagnetic spectrum moves at this speed of 3.0 times 10 to the 8 meters per second. Now that is as fast as anything can move in the entire universe. So that's the cosmic speed limit. And light has the privilege of traveling at that speed. Now, when it comes to the nature of EMRs, so we talked about Hertz briefly. He was doing some of that stuff to actually confirm some experiments that Maxwell did. Maxwell came up with some very important ideas when it comes to the nature of electromagnetism. The first one is that EMR is produced whenever a charge accelerates. Now, this is important. This is how electromagnetic radiation is produced. If you think about your body giving off heat, that's a form of infrared. Well, that's because the particles in your body are jostling back and forth. And as things jostle back and forth and change direction, they're accelerating. And so they produce EMR. If we think about, we go back to kind of the northern lights, we have this magnetic field on the Earth. These charged particles come in and they get trapped in this magnetic field and turn in a circle. Well, we know that things that move in a circle are accelerating. That's centripetal acceleration. So these things, they give off electromagnetic radiation. That's what the northern lights is. It is these accelerating charges in the Earth's magnetic field, and so they emit electromagnetic radiation. Another important idea is the speed at which EMR travels. It travels at 3.0 times 10 to the 8 meters per second. The electric and magnetic fields are perpendicular to each other and perpendicular to the direction that the wave is actually traveling. So that is also, that's something we just talked about. That's important as well. There are some other ideas there too, like the frequency that a charge jiggles back and forth will match the frequency of the EMR produced. We'll talk about that just in a second. And then in coming weeks, we're going to talk about some of these wave properties of light, and we'll look more at number 5 at that time. So when we look at EMR, there's an entire spectrum. The part of the spectrum that we're most familiar with is this visible spectrum right here. So this visible spectrum is common to us. We can see it. It's between 450 and 750 nanometers. So that's times 10 to the negative 9 in units of meters. When we talk about the wavelength of the light that we can actually see. Now we have both sides of the spectrum. So we have red light, which is the longest wavelength, 750 nanometers. Infrared is right beside that. That's, you can see that, snakes can see that. We can see that with an infrared camera. It's how heat is moved around, but it's a form of electromagnetic radiation. We can go to microwaves. Microwaves usually measure in units of around centimeters. So these wavelengths get a little bit longer. If you were to put something in the microwave, like something that melts just for like 10 seconds or 20 seconds and then stop it, you could probably see the wavelength of the waves in there, and it will be in units of centimeters. And then if we go beyond that, we have radio waves, which are usually meters or even kilometers long when we're talking about the wavelength. When we go on the other side of visible light, so violet is the shortest wavelength, that we can see. Outside of that, then we have ultraviolet, which we can't see, but it's what we protect ourselves with. So when we put on sunscreen, we're trying to protect ourselves from UV light. So UV light, we go beyond that and we have X-rays. And then we go beyond that and we have gamma rays. So all of these are forms of EMR, and they follow those same rules that we looked at in the previous slide. They all come from accelerating charge. And the amount of acceleration gives us kind of the frequency and the energy of this wavelength of light. So radio waves have very low energy, very low frequencies, very high wavelengths. So they have long wavelengths and very short frequencies because their wavelength's so long. Remember this one, V equals F lambda. Everything travels at the same speed, so that's C now. But if the wavelength is long, that means the frequency is short. So these radio waves have very low frequencies. They're very low energy waves. Hertz was producing these radio waves when he just turned the switch on and off. So just an electron moving ever so slightly up and down a wire can generate these radio waves. When we get to infrared waves, now these are atoms moving back and forth. They give off infrared, which we kind of call heat. So if I were to heat something up and it were to vibrate, that particle were to vibrate back and forth quicker, it would give off infrared radiation. If we go like to X-rays, X-rays are generated by taking electrons that are moving very fast and then slamming on the brakes, so running them into a piece of metal. So they move very quickly and then they come to a very quick stop. So there's a very fast negative acceleration and we get an X-ray that's generated. But there is a larger acceleration with these X-rays. So we get a higher frequency and more energy with these X-rays. Your project this week is going to focus on EMR and some of its properties and the different types of EMR. But we are going to, this week, focus on the speed of light and where it came from. Now, the speed of light, scientists were kind of interested, okay, what is the speed of light? How can we determine its speed? But a lot of scientists really came at it from a very simple idea. Right, in grade 10 and even before that, we were looking at speed as distance over time. And this is really what scientists were trying to do to determine the speed of light. Now, the problem with light, if we look at the speed of light, it's 3.0 times 10 to the 8 meters per second. That is very fast. I think it takes something like 8 minutes to travel here from the sun, which is a very large distance. So the problem with this, and we're going to look at a couple of experiments that scientists did, is that if the distance was small, the time was going to be very small and very hard to measure. And the other is, in early kind of history, it was hard to measure very large distances. So we're going to look at how scientists used the simple idea in order to actually get at the speed of light. Galileo tried to measure the speed of light by standing with an assistant on a near hill. So they took their lights, kind of like a flashlight. They would turn them on and off, so they'd open the door, close the door, open the door, close the door. And they tried to get used to that timing. And then they went on distant hills at night, and Galileo tried to gauge if there was a difference in the time of opening and closing than what they had been practicing. And he couldn't really determine anything. So the problem when Galileo was doing this is he had a very short distance. The distance wasn't nearly large enough to discern a difference between the amount of opening and closing or turning on a flashlight, turning off a flashlight. So his experiment didn't really work out. He couldn't really get a good number for the speed of light. And he said that it was probably infinite. Then actually we had a relatively accurate measure of the speed of light. And this came from looking at one of Jupiter's moons, Io. So Ole Romer was an astronomer. And what he noticed is that Io, when Jupiter eclipsed Io, the amount of time that it would take to reappear depended on where the Earth was in its orbit as well. So he noticed that there's a difference in the amount of time. So there's a difference in the amount of time for Io to be eclipsed by Jupiter when the Earth was closer to Jupiter or when the Earth was farther away. So there's kind of this distance here. So he was actually able to measure a speed of light that was relatively close and allowed him to make predictions. And actually he got into a competition with the head of the Royal Society, and he made a prediction about when Io would reappear. And this other guy's like, no, you're crazy. It's not going to make a difference. But Romer was able to make a very accurate prediction, and he actually won that bet. They still didn't believe him, and I think he ended up dying of some horrible disease, like on the street. But he did get a relatively good measure for the speed of light for the time. There is a video that I'll include with more information about this experiment in kind of the videos for this week that you can kind of watch along with that if you're interested. Using like Romer, using the difference between the distance of the Earth from a planet and the amount of time it takes to eclipse. Then we got into some more accurate measures of the speed of light. This is Fizeau. He used a tooth wheel. If you want to see this experiment, watch the Adam Savage video that I'm going to post in this week's videos. He talks about scientists using very simple ideas to measure complex things. And he talks about Fizeau's wheel, but he had this toothed wheel. So he stood at this distance and he saw that he lit this candle. So there's a candle. And he found that as that wheel spun, this candle started to get closed off until it was completely covered. And so what he could see is he could actually see the teeth of these wheels, the teeth of this wheel. So knowing the speed of the wheel, he was actually able to get a relatively good measure of the time. Is that it's less dependent on, okay, when is it fully covered, when is it not fully covered. The moon, Michelson came and he improved this with an experiment that we sometimes do calculations with, where he used a rotating mirror. Now, the reason why a rotating mirror was better, you can either see the light or you can't, because that angle's either good or it's not. So once this mirror has rotated an eighth of a turn, then the light can reach the observer and they can see it. And so this is what Michelson did. So he kind of took this, he used an 8-sided mirror, and he was able to get an extremely accurate measure for the speed of light using this method. So it looked like this. So he had a light source. It went to a mirror that was 35 kilometers away, and then came back to the mirror and bounced to the observer. And then so here's a Michelson experiment type question. So he did that experiment. So he was using these ideas. Now the distance it traveled, because it went there and back, was 70 kilometers, right? So this is 70 times 10 to the 3 meters is how far that light actually traveled. The thing that was very, that was interesting and very ingenious about his experiment was how he actually measured the time. So this mirror was rotating at 32,000 RPMs, which maybe isn't the most useful. What's probably more useful is dealing with it in terms of hertz. So that's 32,000 rotations per minute. And if I want to know the rotations per second, so I know 1 minute is 60 seconds. So this is 32,000 divided by 60. So this is spinning at 533 hertz. Now what we want to know, though, is the amount of time for one complete revolution. This is frequency, and if you remember, the time for one complete revolution is called a period, which is 1 over the frequency. So 1 over that, so my answer to the -1, so my period is 0.001875 seconds. And for this experiment to work with an 8-sided mirror, it's rotated 1/8 of a rotation. So the actual time for the light to go there and back is 1/8 of the period. So I take my period and I divide by 8, and I get 2.34 times 10 to the negative 4 seconds. So this was actually, you'll see, 2.34 times 10 to the negative 4 is a very small number. So he did not get around this light measuring problem by going over a large distance like Romer did going to Jupiter and back. But he was able to actually get a very precise measurement for time over a short distance. And he was able to do that with a rotating mirror. So when we calculate that, so 70 times 10 to the 3 divided by my answer, he got a speed, so our speed of light here is 2.99 times 10 to the 8 meters per second. So there are some speed of light calculations that you'll be doing this week. They are using this very simple velocity as distance over time, but coming at it from some different ways. Some are using rotating mirrors or toothed wheels to actually get a very accurate measure for time.